Well, one of the things that I'd like you to do is just take a piece of paper, write your name down on it, and give it to me. You leave today, just so I keep track of who's here. I don't take attendance in general. Meaning classes.
I can like.
Okay, so let me start off with some basics in here.
Sorry.
I just want to say a couple of things about the syllabus. Oh, just in case. 4120, Abstract Algebra. That's me, Jim, something or other, anyway. You're welcome to use that part of my name. My office is in Long Hall, 205, hours this semester. 7 to 8 a.m. Monday, Wednesday, Friday. Although that 8 really probably should be about between 7:45 and 7:50 because I gotta flip it over here. 10 to 1 Wednesday, and 10 to 2 Monday and Friday. So say what you will about me. I am fairly generous with my time. That's a lot of office hours. I would encourage you to take advantage of them. And if they are inconvenient for you somehow, please communicate that to me as well. I certainly also always have the option of coming out early because I'm usually here at about 5:30. So just let me know if those are any problems. See where they're highlighted from the syllabus we have. The syllabus stuff, all the stuff is up on Canvas. So in this class, so we're going to have 2 exams and a final. The 2 exams will be 15% apiece of the final, and homework. And the homework you might think is sometimes excessive. It'll be due once a week. There might be an exception, but you can pretty much count on that. I'm going to work you hard on this. So let me be absolutely clear at first. The homework's going to be tough. You're going to have to work on it. This is the only way to learn the class. Do not get discouraged by it. I and the grader are going to really stick it to you, right? You can expect to get a lot of marks off on your homework. The reason for this is not because I hate, it's because I love. I don't want you getting back perfect scores on problems and think, oh, well, I did it great, but there's subtle little problems there. So the default will be to be hard on you. To make up for this, your homework average will be curved around a rather benevolent mean. So if you're in the middle of the pack, you're probably getting at least an 80. And I am pretty transparent about the grade. So at any point, you can come up to me in the semester and say, hey, Jim, where am I? I can tell you where you are, right? What your homework average is with the curve and the whole 9 yards. So just, and of course, the grades will go up on Canvas. Do not trust any Canvas generated numbers. They really don't even know how to add and multiply there. Only trust numbers that I put up there in the column. After each exam, I will give everybody an update on what your predicted grade is, what your overall average, the whole 9 yards. At any point in between that, you can ask me what an update is, but whatever the Canvas is doing, just don't pay any attention to that. The exams right now are scheduled for tentatively for Fridays. Friday, the first one, February 13th, the second for April 3rd, and the final exam is just on your schedules, whatever the registrar says. I believe it's Thursday, finals week from 11:30 to 2 p.m. Also, after each exam, so you'll get these weekly homeworks. You'll get some extra credit homeworks too. After every exam, you have the opportunity to come talk to me, talk about where you're at in the course, right? Yes.
What was the first date on that February exam?
It was 13.
13. Okay, thank you.
So after every exam, you'll have the opportunity to come talk to me, talk about, where you're at in the course, what your goals are. Just for showing up and doing that, you get a free extra 100 extra quiz score. If you don't do it, you're not punished, but you don't get the reward either. So make sure that you do that and take advantage of the opportunities in here. I have a grade scale set, 90, 80, 70, 60, like that. It'll be, so here, this is a test on your 3190. It says on my syllabus, if you get a 90 in this class, you will get an A. It does not say if and only if, right? So remember what that means from 3190. There may be a curve to the class, but you need to live your life like I'm going to do what it says on the syllabus. I will maybe be nicer than that, but you need to aim for those goals here. So I do not, as I said, require, I'm checking on who all's here the first day just to kind of make sure that I don't have any lost sheep. As a general rule, I don't take attendance. You all are all adults. For the love of God, please come. Well, I'm telling you, it covers a multitude of sins, right? Just being here, sometimes I know it's early in the morning, et cetera, et cetera. If you just be here, it'll patch things up. I highly recommend it. I record on such occasions as, maybe you got sick or who knows what else. I record the lectures as technology permits, right? I can't guarantee that it's not going to go wrong. And I post them up on the Canvas page and on my YouTube channel. So you've got the recordings to look back at. And actually, even if something goes wrong, I've probably got some more recordings as well. So, right. So I've expanded on my AI policy there. How many of you all, come on, fess up. How many of you all have used AI? Oh, come on. I have. Everybody, look, don't do it in this class, right? I mean, I'm not going to be out there to stop you or anything else, right? Again, I'm not going to like pop up in your dorm room and say, are you using AI? That's not going to happen, right? It is going to hurt you to do it. And AI can be very deceptive. One of the things about all these AI things, they said, oh, yeah, here's the answer. Lots of times it's not. There are mistakes. So really the best resource, look at the person next to you. This is the old college joke. Look at the person next to you on either side. There's your best resource. You all are all math majors. You should get to know each other. I highly encourage you on the homework to form groups, work together, criticize each other, et cetera, et cetera. I encourage this working on homework. My final rule is when you submit your homework to me, which you will upload every week on the Canvas thing. When you submit the homework, I want to know what your take is on whatever discussions you've had with your friends or whatever else. I don't need to know what your friends say or what ChatGPT thinks. I need to know what you think. So here's my rule. The homework problems are either graded on a 3 scale or a 5 scale, depending on the problem. If I or the grader thinks that you have maybe gone over the line with AI or your friends or whatever, you will get a 0 on that problem or problems that you offend on. Now, I know that it is possible that I might be mistaken, so there is an appeals process. From 1 week from the time that you get a 0 on any subset of the problems, you can come to my office and appeal, and the appeal will consist of me giving you one of these things and you going to the whiteboard and showing me you know how to do the problem, right? So anyway, and even if you don't, there's no death penalty in this class. So, but anyway, so I want you all to work together. I want you to avoid AI because it's a bad idea. And I need to see on the homework what your take on the problem is. Homeworks will be due like once a week, generally, and let's see all the rest of this. Okay, so I think I've kind of covered basis of what I want to communicate. The syllabus is again up online. Oh, and also I want to tell you a couple of things. Every homework, except for this one that I've already got posted, I will put up. How many of you have done anything in LaTeX yet? You typed up stuff in LaTeX? Okay. I don't demand that you do this in this class, but I think it's a good idea for you to at least try it. So one of the things I do when I put the homework up is I give you the homework whatever the homework assignment is on a PDF. And then I put up also the file that's the tech file that I use, the LaTeX file that I use to make it. Because the best way to learn LaTeX is by stealing. So you can take my file and, it's actually simple enough to where you can kind of, I think, get the idea of how it works. If you want to learn how to start typing in LaTeX, it is incredibly useful. And this is a good chance for you to start. I don't demand that your homework be turned in, but I suggest that you try to learn it because I think it's an important thing. So that opportunity is there for you. And finally, there is a first homework that will be due Friday. You may or may not have seen it, but it's very easy. I mean, literally, I ask you in there, what's your math history, classes you've taken, what kind of experiences have you had, and what do you want to get out of this class? I want to hear what your goals are for the class. Just turn in something. This is a 1-0 homework. So, okay, that's what I wanted to cover for right now. How about you all? Any questions? Questions about the nuts and bolts? All right. Well, welcome to Abstract Algebra. This is one of the coolest classes ever. It is the study of basic mathematical structures, right? The integers, one of my favorite mathematical structures. It's a place where you can add or multiply, as a matter of fact. So you've got operations on the structures here. And speaking of the integers, this is where we start. I'm going to start with some of the basic properties of the numbers that you've seen and some functions to kind of remind you. So you've probably seen a good chunk of this stuff before. Let me go over some notations and definitions. Means the natural numbers. 1, 2, 3, 4, forever and ever. And sometimes I'll write this. This is the natural numbers with 0 thrown in. Sometimes that's convenient. This is the integers. It's sort of like the natural numbers grew a tail, right? It's just all integers, positive and negative. Rational numbers. This is the set of fractions, where fractions of integers, integer over integer, where the bottom is not 0. Notice that this includes the integers. This is the real numbers along the real line, like you used to from calculus. And this is the complex numbers. Which is the set of all numbers a plus bi, where a and b are real numbers, and I is famous square root of -1. Have you all seen these notations before? Okay. Another thing that's going to come up after a bit when we talk about algebraic structures, a lot of times when we study these structures, one of the things that's useful to help study them is the functions between them, right? It's just like in calculus, continuous functions, you often use those to study things. Here we use a different kind, but if you have a general function, so suppose I have two functions, f that goes from a, b, and g that goes from b, oh, I'm sorry. I didn't read my own notes. I want g actually go b to c. I want to pick g up where f left off. Given these functions here, here we have the image of F. So probably a lot of you have seen the notation here. The image of F, this is sometimes called F of capital A. And all this is this is just the set in B that you get by plugging in every possible thing in A and just collecting them all. It's a set of all F of A as A runs through it. If you have a subset of B, so if you have a subset D inside B, then F inverse D anybody know, this is sometimes called the preimage of D. Anybody know what this is? Here's a little subset here. This is just the preimage is the stuff that lives in A that lands in D. But this one, for example, it was just all the stuff back in the original domain that lands in here. This guy doesn't land in D, so it's not in the preimage. And finally, I'm going to define the composite function. Let's see, I guess I do that first. Oops. Yeah, right. So if you do, this goes actually from A to C. And it's just sort of like, it just had a little train stop in the middle. So the composite function is you just get on board at A, see where it ends up in B, and then plug that into G, and that gets you where you're going. All right. So if you look at the so the F of A, this is G of F of A. Okay. Any questions on it? Yes.
What's the set notation of the, called it the before image F inverse of D?
I'm sorry,
The second thing you wrote down on the first board, could you finish the set notation for that?
I didn't finish, did I? I got so excited about my picture. This is all the A and A such that F of A is empty. There we go. Thank you.
Oh, that the after image or the?
Right. This is sometimes called the pre-image of D, and sometimes under F, because that's the relevant function there. Okay. One, F is 1-to-1, injective, sometimes it's called. If anybody remember what it means to be 1-to-1?
Everything in A corresponds to at least one B.
Close. This means that F of A1 plus F of A2 implies A1 is equal to A2. Right? So in other words, this is equivalent to A1 is not equal to A2 implies F of A1 is not equal to F of A2. So you can't have two different inputs giving the same output, right? Right there. So in other words, this is not 1-to-1. If you have two different inputs going to the same output, that's not 1-to-1. If you always avoid it, it is 1-to-1. Okay. Anybody remember what it means to be onto? Yeah.
The image of the domain is equal to the codomain.
Okay, actually, that's a fancy, no, that's good. That's a fancy way to do it. I'm gonna give his, if the image of F is all of B. So let's say F is. Right, so it's exactly what he said. The image of F is the entire codomain, right? But well, that's kind of sophisticated. So since my parents are cousins, I'm gonna do it more simply. If B is any B and B, then there exists A and A such that F of A equals B. No B and B is lonely. There's always some A that goes to it, right? Three, F is bijective if F is both injective and surjective. And bijective maths were probably important when you were in 3190 because it was how you counted sets, especially ones that were infinite. And finally, number 4, sure, my left and right here, correct? F has a left. Let's has a left, respectively right, inverse. If there exists an H from B to A, right. If and only if there exists an H such that H composed with F, the identity of A, respectively, F composed with H is the identity. And here, by this notation here, I mean the identity function on A that takes everything in A to itself. So a function can have a right inverse, a left inverse, and probably in 3190 you looked at invertible functions that have both the right and left inverse. Now bring this last definition up for a reason. So I'm going to couch all of this stuff in terms of functions here. one. F is 1 to 1. So injected. Where if and only if F has a left inverse. So if it's injective, it has a left inverse, and conversely, two, F is onto or surjective, and only if, anybody want to guess this one?
Has a right inverse?
Yes, that's right. And so, without thinking too hard, I guess I can make a third one. It's injective if and only if it has a left inverse. It's surjective if and only if it has a right inverse. F is bijective if and only if
Has left and right.
have a left and a right inverse. Actually, in this case, it'll be the same thing. And actually, I'll say something stronger. There exists G with B to A such that G F is identity of A and F G is the identity of B. Right. And finally, let me take a special case here. Suppose F goes from A to B and A and B are both finite sets. So I'm saying a couple things here. So I've got a function from A to B, and I'm saying that A and B are of the same size and they're finite, right? Then F is injective if and only if F is surjective if and only if F is bijective. Now let me make a couple of remarks here. If you have a bijective function, it is always surjective and it's always injective, right? I don't expect these two to be equivalent in general, but here's the key. These two sets are the same size and they're finite. Notice if you remove the fact that these two sets are the same size, this theorem is no longer true. And even if they're the same size in infinite sets, these are not equivalent anymore. So this is very specific to finite, right? I mean, A has 5 things and B has 5 things, right? Now, if I were to make an injective map from here to here, I can never pair up. So this has to go somewhere. Now, where does this one go? Well, anywhere except for this one, right? So maybe it goes here. This can't go to any of these other two because it has to be injective. So maybe it goes here. This one has to go somewhere new. So does this. Notice that because of the fact that the sets are the same size, the injectivity gives also none of the stars are lonely. right? So it's onto as well. If I had an infinite set, I can easily make something that's injective, but not so. For example, if it went on forever, I can certainly do this. Right? And this will be an injective map. It's not surjective because this one's lonely. I could also do this. This one is a surjective map that's not injective, right? So if the sets are finite, it's game over. Okay. Any questions so far? Okay, so that's a quick review of functions. There's another thing that we need to talk about, and that is relations. These are important in examining things in algebra. I love the definition of relation when you first get it, because on the surface of it, it's fairly simple. Let A be a non-empty set. You can expand some of this anyway to sets that are empty, but let's not bother. A relation R on A is a subset of so in other words, R is just some subset of A cross A. It could be the whole thing. Or it could be the empty set, right? A is not empty, but the relation would be the empty set. It could be every ordered pair of the form A comma A. There's lots of things that you can do. There's lots of relations. We write A is related to B if and only if AB is in the relation. So if the ordered pair from A cross A is in the relation, then we say that A and B are related. We use a little squiggle to say that they're related. Note that well, we say squiggle is number one, reflexive. If A is related to A for all A and A. So in other words, if you always have the order pair A comma A in there. Two, symmetric. If whenever A is related to B, then B is related to A. And transitive. If A is related to B, B is related to C, means that A and C are related. So let me give you an example of a relation that is reflexive, symmetric, and transitive, right? I'm going to let my set A be the natural numbers. Right? And I am going to declare that two natural numbers are related if their difference is even. Right? So let's see. Would 2 and 3 be related? No. Well, what about 3 and 5? Difference there is even, so they would be, right? Well, let's think about this, right? Is any number related to itself? Well, take a number, call it A. A minus A is 0, which is even. So yes, that little relation that I said is reflects it. If A and B are related, that means A minus B, say, is even. Are B and A related? Well, B minus A is just the opposite sign of this. So if this first difference is even, then this one's even as well. So yeah. Let's say that A minus B, let's say that A and B are related. That means their difference is even. And B and C are related, so their difference is even. Let me add these up. A minus B and B goes away. So notice A minus C is even. So actually, the relation that I gave you is the relation I give you satisfies all these. They're reflexive, symmetric, and transitive. Right. Here's another way. Let's let our set be real numbers here. All right. So just consider the real numbers. I'm going to say that A is related to B if A is less than B, strictly less than B. So I'm going to say that, so 2 is related to 3, right? And 3 is related to 17, right? Because it's less than that. Is that one reflexive? No, it's not, because 2 is not strictly less than 2, okay? So that's gone. Is it symmetric? Well, it's not symmetric either, is it? Is it transitive? Let's suppose A is strictly smaller than B and B is then A is strictly smaller than C, right? I could have changed my less than to less than or equal to, and I would have picked up reflexive, right? But that's still not going to pick up symmetric. Everybody see that? Can anybody give an example of something that's not transitive? How about two college football teams related if one of them beats the other? All right. That's certainly not transitive. And as Clemson students, you have seen that time and time again, right? And in fact, football would be kind of boring, wouldn't it? If, you know, if it was transitive, if this team beats this one and this other team beats this one, then the teams A and C don't even need to play, right? Because we know that C would beat A, but that's not what happens in real life. Yeah. Tilde is reflexive, symmetric, and transitive. Then tilde is called an equivalence relation. How many of you have seen equivalence relations in like 31 minutes? Right? This is an old friend, or maybe an old enemy, I don't know. Continuing on with this school of thought here. If tilde is an equivalence relation on A, then, and let me throw something in, and A is an element of A. You've got this equivalence relation on set, and then you've got some element in it. The equivalence class of A here's some notations that you might see. A modulo equivalence. I'll usually just write it this way, just a little box around the A. This is the set of A and A such that A, or I'm sorry, I should write X. So the equivalence class of A is just a set of everything in the set that's equivalent to A. Now I know that there's one thing in that equivalence class for sure. Can anybody tell me one thing that will be in little box A? A itself, right? Because since this is an equivalence relation, A must be equivalent to itself, so it's got to be in its own equivalence class. If you think back to that example that we did a moment ago, remember how we said two natural numbers? I'm going to say that they're related. Actually, we showed that that's an equivalence relation. We'll say that two natural numbers are equivalent if their difference is even, right? Let me pick a number. 26. What can somebody describe to me what the equivalence class of 26 is? Well, I bet it's got 26 in it, so we've got that. But what else?
Relation are we talking?
I'm sorry?
Relation are we talking about?
The one where two natural numbers are related if their difference is even. That is correct. Every even number is related to 26, right? Okay, so at least all the evens are in there. Are any odds in there? No, because 26 minus an odd is always going to be an odd. So none of those. So actually the equivalence class of 26 in that case would be all the evens, right? What's the equivalence class of 1? All the odds are equivalent to 1 because any odd minus 1 is even, right? Notice. And what's the equivalence class of 8675309? That one's odd, so all the odds as well, right? Notice that those two different numbers, 1 and 8675309, have the same equivalence class, even though they were very different numbers. And notice there's no evens in those equivalence classes, so there was no overlapping between the equivalence class of 26 and the equivalence class of 1. Right? So let me give you this last one, so maybe it won't seem like it's come completely out of the blue. A partition of a set A, and I'm assuming set's not empty, is a collection of subsets So when I say a partition, it's just a collection of subsets of set A that have basically two properties. By the way, anybody know what these two properties are? What does it mean to be a partition of a set? You might remember that from the good old days.
Subsets intersection is zero.
Okay, that's right. And one more thing. Actually, you got the hard one. That's right, right. So I think of A as a jigsaw puzzle, right? Everybody's worked a jigsaw puzzle at some point, right? What is a jigsaw puzzle? It's a partition. You've got your whole puzzle, which is A, and it's cut up into these little jigsaw pieces. And if you've ever had jigsaw pieces that overlap, you've got problems. You need to send that back to the manufacturer, right? It's got these two problems. Number one, the union of all the AIs is A. So that means when you put the jigsaw puzzle together, you get the whole big picture that it shows you on the box. And two, this is the condition you said, if I and J are different indices, then AI intersect AJ is the empty set. So two pieces of the partition are either exactly the same or there's no overlap at all, right? And again, you'd have a hard time putting together a jigsaw puzzle on your kitchen table if that were not the case. Okay. Let me give you an example. Let's let A be the natural numbers. Let A1 equal A2. This is a partition. Because if I put those two sets together, I get all the natural numbers and there's no overlap. Notice that these are precisely the equivalence classes that we discovered earlier. And this, my friends, is not a coincidence. Let me give you the following. And you've probably seen this. Right? Let A be a non-empty set. Number one, if tilde is an equivalence relation, on A, then the set of equivalence classes under this relation, equivalence relation, forms a partition of A. And the converse is true in the following sense. Two, if the collection AI partition of A. So suppose that I start off with a partition, then there exists an equivalence relation. Tilde on A such that the equivalence classes under tilde are precisely sets AI. Okay. By the way, anybody want to guess how this the equivalence relation should work? I'll let you think about this. I'm gonna leave one definition. We'll say that A is equivalent to B if and only if A and B are in the same AI. It's almost like cheating because I take the AIs and I just say, okay, any two of you that lie in the same AI have to be equivalent. Okay, so next time we're going to be talking about properties of the integers, but let me give you this final definition, something to think about for next time, just for fun. Let A be in the integers. We say, I say that A is not zero in my notes, but you don't need to say it. Let A and B be integers. We say that A divides B. What does it mean for A to divide B? What's your intuition tell you? I mean, if I asked you, does 5 divide 10? What would you say? Does 5 divide 8? Not in the integers. Why not?
Number C such that 5 divided by 8 is equal to something C in the integers.
Right. So 5 divides 8, but not cleanly. Like you get 3.6, which is not an integer. So what does it mean for A to divide B? If there exists C in the integers such that B is equal to AC. Now, like I said, I wrote in the definition, my definition, that A is not zero, but you don't really need that. In fact, more properly, that's our best definition. Yeah, you might ask yourself, what does zero divide? You might get an interesting answer. So that's something fun to think about. Talk about the integers next time. Any questions? Don't forget to write your name down and give me a piece of paper with the name on. And I will see folks next time.
Sure.